We now want to move on to the true purpose of dot products, which are what are called projections. We're going to look at a projection of the vector u, shown on the screen, onto the vector v. What we're really interested in knowing is how much of u is in the v direction. So if we were to drop a perpendicular line here, we're interested in knowing how much of u that you see there is in the v direction. And we're going to refer to that as the component of u in the v direction. So we already know from our last lesson that if we have a vector u specified by its length, u, and then the angle from some axis, theta, then the distance here in blue is u, length of u, cosine theta. So the amount of u in the v direction is the length of u times the cosine of theta. Another way we can write the cosine of theta is using our previous theorem. Cosine of theta is u dot v over the magnitude of u times the magnitude of v. The magnitudes of u cancel. And one way we can write this is u dot v over magnitude of v. And that's a unit vector in the direction of v. And so the result is, if you're asking how much of u is in the v direction, well, then you dot u with the vector that represents the v direction. So this is a unit vector in the v direction. Now that tells you the distance that u has in the v direction, but it doesn't tell you the vector of u that's in the v direction. That's called the projection of u onto v. So instead of just the distance, we want to think of u as being composed of two vectors. This first vector in red is the part of u that's in the v direction, and this second vector in orange is the part of u that is not in the v direction. And the sum of the red vector and the orange vector would give you then u. So the projection of u onto v is the part of u that's in the v direction. Well, we already know how much of u is in the v direction. That's u dot v over magnitude v. And now we just need to put that vector in the v direction. So we're going to multiply that scalar number, that amount of u in the v direction, times the unit vector in the v direction. So this is the red vector that you see in the picture. It's the amount of u in the v direction times the vector that's in the v direction. Now the book will probably write this as u dot v over magnitude of v squared times the vector v. And that is a perfectly valid way to write this, but it doesn't illuminate what the projection of u onto v is. It doesn't show you that it's that component of u in the v direction times the v direction. So let's proceed with an example finding the projection of u in the direction of v. So I'm given two vectors, u equals 4, negative 5, 3, and v equals 2, 1, negative 2. I want to find u in the direction of v. So I'm going to start by trying to figure out, well, what is the direction of v? So what first is the length of v? The length of v is the square root of 2 squared plus 1 squared plus negative 2 squared. Adding those up, that's the square root of 9, or 3. So the unit vector in the same direction as v, if I divide v by its length, 3, is going to be the vector 2/3, 1/3, negative 2/3. So that vector will be help us in finding the component or the amount of u in the v direction. So we're looking for u dotted with the unit vector v, and that dot product is going to give us the component of u in the v direction. Okay, so the dot product is going to be then 4 times 2/3 plus negative 5 times 1/3 plus 3 times negative 2/3. Now, the denominator for all three of these is going to be 3. Looking at the numerator, I have 4 times 2, which is 8. I'm then going to subtract 5. That will give me 3. And then I will subtract 3. That will give me, I will subtract 6, and that will give me a negative 3. So the amount of u in the v direction is negative 1. Okay, now we're going to proceed with the projection of u onto v. That projection is going to be the component of u in the v direction times the v direction we already computed u dot v over magnitude v as negative 1. So this will be negative 1 times the unit vector v divided by magnitude v. So in other words, this should be negative 2/3, negative 1/3, 2/3. And so the idea, if you're kind of looking at the picture that we had above, is that part of u is pointing in the v direction, and the part of u that's pointing in the v direction is negative 1 times the v direction. We'll now move on to our last example, which is from physics, and that is the example of work. So the work done in moving an object, we said, was force times distance, but in more dimensions, it's actually force dot distance, or the magnitude of the force times the magnitude of the distance times the cosine of theta. So work is the product of distance that an object has traveled and the force applied in the direction of motion. Remember that F cosine theta is going to be the amount of the force in the direction D. So I have a short example. Find the work done by a child exerting a constant force of 20 pounds at an angle of 30 degrees to pull a sled 1 mile. So a child is pulling a sled, and he's pulling it by a string, which you've seen that I've drawn in blue. And because he's pulling it by that string, he's pulling it at an angle of 30 degrees. He's using a constant force of 20 pounds. So how much work is the child doing? Well, we just need to do force dot distance, and that we know is the magnitude of force times the magnitude of the distance times the cosine of the angle between them, 30 degrees. So this is 20 pounds of force times pulling the sled 1 mile, or 5,280 feet. We will need this to be in feet to get the correct units for our answer. And then the cosine of 30 degrees is the square root of 3 over 2. Multiplying that out, we're going to get 52,800 times the square root of feet, square root of 3, and that is in the units of foot-pounds, which is the correct unit of work.